Hi, back in December of 2016, I published a video on our YouTube channel about a pending and upcoming problem with the transformers that are used with NuTone IM and IMA4406 master stations. The short version of that video, which I will put a link to down in this video's description, is that the 4406s use a very special transformer that NuTone made, and those transformers are no longer made, and NuTone no longer has any of them, and they are becoming almost impossible to find. I don't think I have found any for sale in the last 3 months, and I've had a lot of people call me to see if I have some because they need them. And the thing that makes these transformers special is the voltage and the wattage that they produce, and because of the size of the transformer, they have built inside of them, inside the cover here, they have a built-in internal fuse. And if you happen to accidentally short across the low voltage screw terminals on the transformer, you will blow the fuse. Or if your 4406 master station has some kind of really dramatic problem or failure in it, it can overload the transformer and blow the fuse. And the fuses are a safety device because you don't want something, there's two of these in a 4406, and each one has the ability to produce about 4 amps of power, which is a lot, and you don't want something like this in your wall that could potentially cause a fire. These transformers are UL approved transformers for their installation location and their use, and having the internal fuse is part of the necessary safety device in its design to meet the UL requirements. So having the fuse is necessary and important because it's an important safety device. What happens to transformers when they blow the fuse? Well, you blow the fuse, the transformer goes dead. There is no output here anymore, and it won't power your IM or IMA4406 master station, and then you have to search for a replacement. Lately, these have been selling for, when people buy them from us, they're upwards near $100 a piece because they're rare and hard to come by, and whatever is available as new is rapidly running out. So in the other video I went over this, and then in a subsequent video I showed how we were able to construct a replacement transformer from a more generic chassis mounted transformer and put it into an enclosure, but that would only be for installations that have remotely mounted transformers, not for the original type of installation where these are in the wall housing in a transformer box inside the wall behind the master station. Since those videos, I've put a lot of thought into how could we possibly construct replacement transformers that are the right ratings, the right voltage, and the right wattage for people that need them, and install them inside the original wall housing where most of these are. It turns out that that's a very complicated thing to do, and it involves a lot of complicated small manufacturing, and there's a lot of inherent problems with trying to do something like that, not so much from a technical point of view, but trying to design something that would be easy for the average homeowner or electrician or some person who doesn't do this all the time, is not really that familiar with it, to be able to install easily and have it be safe. And safety is a primary thing when you're talking about any type of power source, even the lowly class 2 transformer. About 6 weeks ago or so, I had an opportunity to repair, and this will seem totally unrelated, but it's not. I had an opportunity to repair a customer's vintage NuTone door chime base, and his door chime base was made around 1936. And one of the things that was very unusual about that door chime base was it had its own low voltage transformer built inside the chime box that would be mounted on the wall, and therefore that type of installation would have had 110 power from the house electrical circuit wired into the chime box, which would never work today with today's electrical codes, and it had a transformer in there. So part of the rebuilding and refurbishing process on this fellow's chime was I had to do something with the primary wires. The primary wires are the wires of a transformer that carry 110 or 115 volts, and because that particular transformer was from 1936, the wires were the old-fashioned woven cloth-covered type wires that you would see in a really old house, like the turn of the last century kind of thing. And the coverings on those wires had dried out and cracked and become brittle and were falling apart, and it wouldn't have been safe for him to reinstall it and hook it up to 110 power with cracks in the insulation. So I had to do something with that to make it safe so he could reinstall it. And the only way to do that was, the only reasonable way to do that I could see, would be to take the transformer out of the chime case, disassemble the transformer, and replace the wires with new wires that would be modern and safe. Fortunately, the transformer came out easy, and it was a different design than something like this. It had sort of a strap that went around it, and then on the bottom there was a tab, and it went through a slot, and you held it closed, and you bend the tab over, and that held everything together. And that was the part of that chime rebuild that I was mostly dreading, because it's an irreplaceable transformer. It's not like anything made today because it's 80 years old. I actually put it off to the very end to deal with, and then when I actually went to do it, it actually was really, really easy and really, really simple. And it occurred to me after I had done that, well, if I can take apart an 80-year-old transformer and repair it and make it safe, why can't we take apart one of these? This is a modern transformer. It's made in a modern fashion. Yes, it is different than the 1936 transformer, but transformers are transformers are transformers. So let's not get silly about it. Let's see what we can do. I've actually done one of these already, and today in this video I'm going to show you how we can repair 801T NuTone low voltage transformer with a blown fuse. How about that? I think it's something. Anyway, so let's get on with it. This will probably be long because I'm going to try to show you all of it that I possibly can, and I'll try really hard to keep my big giant hands out of the way so you can actually see what I'm doing. So briefly, let's go over the anatomy of a low voltage transformer. It's actually pretty simple. It's a big heavy metal cube. You have laminations here in the center. This is the core of the transformer. You have two sides to every transformer. You have one side which is called the primary side. The primary side is the side that gets hooked to the high voltage. In this case, your house electrical wiring, which would be 115 or 120 volts usually. Then you have the secondary side. The secondary side is the low voltage side of the transformer, and it doesn't matter what the low voltage is. It can be a 6 volt transformer or a 16 volt transformer or an 18 volt transformer or a 24 volt. Anything up to, I think it's 70 volts is considered low voltage. But for NuTone systems, 24 is the highest you ever see. So this is the low voltage side, and you have the low voltage screw terminals here, and this is where the red and white wires that come from your 4406 master station would be connected. The first thing we have to do is to disassemble the transformer is inside, and you can maybe see on the low voltage side of the transformer, you have this sort of reddish cardboard insulator, and it's held onto the end cap here with these little rivets. And no, we're not taking the rivets out. And then you have these two metal tabs, and they're threaded to accept the two screws where the wires go underneath. And if you look here and here on the metal tabs, you have these sort of blobby things. The blobby things are solder. And actually underneath the solder there's a hole in each metal tab, and there's a wire that comes from inside the transformer through the hole, and then it's soldered to it, and that's how the voltage gets out of the secondary windings into the screw terminals. So the very first thing we have to do is we have to desolder this, because when we take the transformer off, we have to take this end cap off. And to get it off, you have to desolder these so the wires aren't holding it in place. So that's the thing we're going to do next. or first, I guess. Okay, so sometimes when you have to desolder something that's large and heavy like these tabs and screw terminals, and no, I'm not taking the screws out because they really don't want to come out all the way, so we're just going to leave them there. Sometimes a good thing to do is to add a little fresh solder to the old solder, because when we go to desolder it, it will make it heat up and flow better, and it'll be easier to get apart. So I have my soldering iron, and all I'm going to do is I'm going to heat this up. Oops. These are heavy and they want to fall over a lot, so we'll try not to have that happen. So I'm going to heat these up. I have a big tip, and I'm going to just add a little bit of fresh solder to the old solder, which will make it easier, I hope, to take it apart. So once we've done that, now what we have to do is we have to desolder them. And this is going to be tricky because I have to try to show you and do it all at the same time. So let me put my visor on so I can actually see what I'm doing. And I'm going to try it. So this is, let me zoom out. This is a desoldering gun. And this is it has a heating element and a tip, and it's connected with a cord and a hose, which I'll untangle, and it goes back to the main unit, which is on the workbench, which has a motor and a pump, so it's a suction device, and the tip will heat up the solder, and when it melts you pull the trigger and the suction turns on, and it sucks the solder away and captures it inside here. So it's a professional tool. It's not something that you would typically have around your house unless you do this all the time. So what we're going to do is we're going to desolder the little blobs of solder so we can get the cap off. And hopefully you can see this. Okay, so we have a good first start. What you probably can't see easily is that this one, as near as I can see, seems to be pretty close. You can actually see space around the wire where it comes through the metal rivet, so this side's pretty loose. This side, not so much. And one of the reasons why that is because this wire that comes through this hole is much smaller than this wire that comes through this hole, and you'll find out why that is in a little bit. Also, this one is bent over somewhat, like it came through the hole and someone bent it over and cut it off to make it stay, and that makes it harder to desolder. So what we're going to do now is we're going to use the soldering iron, and we're going to see if we can heat this up some, because it would be easier if we can straighten it out like that. What we want to do is lose the hook and have it stick straight up, which is better now. So you have to heat it up with the soldering iron to melt the solder that's holding it bent over, so then you kind of use the soldering iron as a wedge, which is not really the purpose of a soldering iron, but what are you going to do? And then you bend it back up like this. So then once you've done that, you can use the desoldering tool again and see if you can get more of the solder pulled away, and that's actually pretty close. So we're probably 80% of the way there, maybe a little more, and that's a good start, and we'll deal with the last 10 or 15 or 20% in a little bit. So the next step is we have to open the transformer up. So like most modern transformers, everything made probably since the early 1970s, these are all riveted together. So you've got 4 rivets, 1 on each corner, and they have the cap end of the rivets here. It goes through the laminations, comes out the back side, and it's kind of smashed over to hold it all together. So to get this apart, we have to take the rivets out, and to take the ends of the rivets, we're going to remove, or we're going to drill out the crimped over ends of the rivets. So there's 4 of them, and the easiest way to do that is with your cordless drill and a decent sized drill bit. Now these are, I know for a fact, these are what are called hollow rivets. And hollow rivets are exactly what they sound like. They're like hollow metal tubes, and they have a cap on this end, and then when it's deformed it crimps over the other end of the tube, and that's what holds it all together. And so the easiest way to remove these is, we're not going to drill the rivet all the way out like this. You don't need to do that. All you need to do is drill off the deformed end of it right here. And the easiest way to do that is, you want a reasonably large drill bit like this, so you can see how big this is. Here's a small screwdriver, and there's the really big drill bit. And all we're going to do is, the goal is to drill away the deformed part of the rivet so it's not crimped on, holding it all together. I'm going to do each one of those, and there isn't a lot to show, and I don't know if I can actually show you how to do this. Let's see what we can do. Alright, so here's a close-up. So here's the deformed end of the rivet, and here's the big giant drill bit. We need to get the wires out of the way because we don't want to wreck them. So here's the big drill bit, and what we're going to do is we're going to drill out the end. So all you got to do is place it there so you can see. Alright, so that's the first one, and you can see that didn't take very long to do. If you have the right size drill bit, it makes it go along pretty well. And if I did it right, I should be able to, for the most part, push, watch here, we should be able to sort of pry this out. And once you get it started, it just comes out. Mostly. There you go. You can kind of see the hollow end right here. Now, we don't care about the rivets. We're not going to reuse these, so it doesn't matter if you drill them and mash up the ends and all that. It doesn't really make any difference because we're not going to use these again, so these become trash. I'm going to be back in a minute because I'm going to drill out the other 3. It's easier to do it. Just get it done because you already saw one, so you know. Alright, I'm back. So I drilled out all the rivets. I removed 3 of them so far. We're going to go ahead and take the last one off, pull it out like this, and now we have taken out our 4 hollow rivets. These are trash, you don't need them anymore, don't worry about them. So now the end caps of our transformer are loose. The back one is loose, and the front one is almost loose. You can wiggle it, but it's not coming off all the way. So how do you deal with this? Well, the easiest way to deal with this, I think, is what's holding it in place at this point is where the wires come through the holes in the metal tabs, and there's a little bit of solder still holding it in place. So the easiest way to do that is, because I don't think we're going to get all the solder out of the hole easily, and what we're going to do is we're going to use our screwdriver here kind of like a little lever, and we're going to heat up the metal tab with the soldering iron. And what this should do is maybe this is awkward because it's easier to do when you're not doing it on camera. That's what it comes down to. So we're going to heat it up, hopefully you can see. And we're going to pull up on the cover while we heat it. And it should let go. So that side's pretty good. I think I got the side with the small wire loose. And now we've got the side with the big wire. And the thing about heating things up with a soldering iron is the more metal there is, the longer it takes to heat. And that's why I've got a soldering iron with a really big tip on it, because it has more thermal mass and that you don't lose as much heat and it's easier to keep up with it. So while I was showing you the soldering iron, the end came off. How about that? So you can actually see holes in it, although they're not perfectly clear and it's hard to show. You won't be able to see it, but you can actually almost see through it. So what we're going to do is we're going to take our desoldering tool while we're working on the end cap, and also while it's already hot, and we're going to try to get out the last little bit of solder so the holes are clear. And to just show you that that's the case, so I have this little wire probe right here, and you can see it now slides through the holes. There's one and there's the other. So holes are clear, wires are loose, like that. So we've removed the low voltage side end cap, and we're going to put that aside. And now we're going to simply remove the line, or the line side of it, and we'll pull this one off and put that aside. And on the primary side of the transformer, there's this little piece of red cardboard insulation material that has holes that the wires go through, and the purpose of that is to keep the wires from rubbing on the edges of the round holes in the end cap so they don't chafe and wear through and short out. And we're just going to take these off the wires to get it out of the way for right now, and we'll put that back on later on. So here's our disassembled transformer. We're not going to disassemble it more than this, because if we tried to do that we would ruin it, and this is really all that we need to do. So what you have here is, now that you can see the whole thing with the end caps removed, you have the metal core, or the laminations of the transformer here, and what these are a whole bunch of really thin metal plates all squeezed together, and then they have some kind of lacquer or varnish or some kind of finish on them to hold them all together. And there's probably, I don't know how many plates there are, but if I just had to pick a number out of my head, I'm going to say there's probably 80 thin metal plates here. And then inside the metal plates, inside the opening in them, is this plastic piece right here. This is often referred to as the bobbin, and if you sew, you know what a bobbin is. And then you have wire that's wound around the bobbin to make the windings of the transformer. And because there are two parts to the transformer, you have the primary high voltage side and the secondary low voltage side, you have two separate or different sets of windings. You have a high voltage set of windings here, and those are connected ultimately to these wires where the 110 goes in, and then you have a second set of windings here, which is the low voltage side. And the thing about transformers is these windings are independent of each other. Other than being wound on the same bobbin, there is no electrical connection between these two halves. The way transformers work is not super complicated, and I'm not going to get into it in this video, but essentially what happens is the high voltage set of windings make a magnetic field when electricity flows through them, and the low voltage side absorb, because it's right next to the magnetic field that the high voltage side is creating, it absorbs some of the magnetic field, and it makes a low voltage end result on the wires. So they are actually electrically isolated from each other. This is in power transformers. There are lots of kinds of transformers, and I'm not talking about all the other kinds. I'm only talking about this kind. So now what we need to do is we need to find our little culprit inside the transformer, which is the fuse that blew. Oh, and I forgot to point out in the beginning of the video, there's a reason why this particular 801T has red X's on the end caps. And everybody raise their hand if you think you know why it has a red X on it. Okay, that's because it has a blown fuse. And that's how we mark it when it has a blown fuse. And that's why I picked it for this video. So let's take a look and see if we can find our fuse. Since the fuse is fusing the low voltage output side of the transformer, these are the wires here and here that we desoldered from the end cap. This, and they come from this half. These are the windings for the secondary part of the transformer, and that's where our fuse is going to be hidden. Most transformers, like this one, they have some type of tape that's wrapped around the copper windings to protect them, and what we need to do is carefully get inside the tape. So what we have here is just an X-Acto knife, and we're going to score this a little bit. And this is not an exact science, but one of the things you have to be careful of is the wire that's used in transformers is often referred to as magnet wire, and it would be similar to, if you remember back in elementary school, if you ever made an electromagnet. It's the kind you would wind around a bolt or something, a metal core, and then put electricity through it, and it makes an electromagnet. So it's the same, that's why it's called magnet wire. And magnet wire is copper wire, but it doesn't have insulation on it. Like, here's copper wire, and it has a red and a black vinyl insulating cover on it. You don't have that on magnet wire because it would make this all too ginormous and bulky. So magnet wire is copper wire, and it has a lacquer coating on it, and the lacquer coating is the insulation to prevent it from shorting out against the other parts of the winding. You know, if you took a bare copper wire and you wound it around something like this and put voltage to it, all the wires are touching each other, and it's just basically a dead short. So it's the lacquer insulation that prevents that from happening. So when we're doing our fuse-ectomy here, we have to be careful because we don't want to scratch or tear or scrape the varnish on the wire, because then we lose our insulation, and that would be bad. So what we found so far underneath the tape, here's another piece of that red cardboard insulator, like here, and there's a lump here, and I have a pretty good idea, I know what the lump is. So if we carefully do this, and I'm not cutting deep here, I'm just sort of scoring the tape and then using the screwdriver to sort of peel it back a little bit. There's something. So we're very close. This must be what it feels like to be like Indiana Jones and you're digging in the desert looking for something. You got to keep digging away at it. You know, if you stop 3 inches short, you may never find it. Anyway, so the tape is stuck on really good, which is the reason it's there. So we'll pull that away, and I'm not going to cut the tape off, so I'm leaving it all kind of raggedy here because we're going to fold a lot of that back over to cover things back up, because the goal here is not only to replace the fuse, but the goal is also to try to replicate this in its originality as much as possible. So here actually, so while I was talking and digging, here's our fuse right here. And if you follow it, this was the wire that was bent up like this, right here that came through the end cap that we desoldered, and that wire is connected to one end of the fuse, and then you have the body of the fuse, and the other one right here, there's another wire at this end of the fuse, and it's soldered on to a copper wire right here. Can you see that? Right here, which is part of the secondary windings of the secondary coil, and this is a heavy wire just like this wire over here. So what they did was they wound the secondary coil with all one type of wire, and then this one was bent out and goes through the end cap and was soldered, and this one, the other end of the coil, is down here at the bottom, and it was folded up, and the fuse is soldered to it, and then it goes out through the end cap. So this is actually, there's a lot squeezed into a little package here. So what we need to do now, and this is the culprit. This is the fuse that blows. When you short your transformer or something happens to it and it goes dead, this is the part that blows. So what we need to do is we need to remove the old fuse, and it seems right here where the connection was made, there's a piece of like braided tubing on it, and that's an insulator also. And so what we're going to do is we're going to see if we can cut this a little bit and take it off, and there it is. And that we're going to keep because we're probably going to reuse it. Now you can see right here, you can see the wire end of the fuse is wrapped around the big copper wire, and it's soldered right here. So guess what we get to do next? We get to desolder this. Now, one of the things I've learned in the other one of these that I did was you don't want to move any of this around any more than possible, because we have to put it all back together essentially as it was. So let's go ahead and desolder this so we can take our blown fuse out. And the way we're going to do this is we're not going to get all fancy with the desoldering gun and all of that, because I don't think we really need to. Although we do need to put on our magnifying visors, because otherwise I can't see it well enough. And what we're going to do first is we're going to take the fuse. The part we don't want to move is this copper wire right here. I want to keep this pretty much like it is. I don't want to bend it around or relocate it. But the fuse I don't care about, because we're going to get rid of it. So I'm going to take the fuse, and it's kind of wound around the heavy copper wire. So I'm going to unwind it some. And then I'm just going to take my soldering iron, and I'm going to heat up the joint till the solder melts. And slide it off. And that's a really easy way to do it without getting all complicated about it. So now our fuse is out, and our transformer is essentially in the same positions as it was. So let's take a quick look at our fuse. This is a fairly standard axial lead cartridge fuse. It has axial leads, means that it has wires on either end. It's a glass bodied fuse, which is what most people would be familiar with fuses, and then metal ends, and inside the glass tube is a very thin metal element, and when too much current goes through the metal element, it gets hot and it deforms and it breaks and the fuse blows. So this is a pretty standard thing. It's got a bunch of tape residue and junk on it, but that's what it is. So what we're going to do is we're going to replace this with something that's similar, but in my opinion is a little bit better. What we're going to replace it with is one of these. This is a axial lead cartridge fuse, but this is a ceramic bodied fuse. So instead of having a glass tube, it has a ceramic body. And it doesn't, the material that the body is made out of doesn't have anything really to do with how the fuse acts or blows or anything like that. It has mostly to do with the fact that this is a sturdier physical construction than a glass tube is. It does cost a little bit more than a glass fuse, but you're only talking about a few cents, so it doesn't matter. And I think it's better if we have to bury it down inside the tape of the transformer there. I think it's better to have a sturdier fuse. This particular fuse is rated at 250 volts, which is common for most fuses, and this particular one is rated at 5 amps, which is the recommended size fuse for a transformer like the 801T, and this is what's called a fast acting or fast blow fuse. There are pretty much two types of fuses in the world. There are fast acting or fast blow fuses, and then there are slow blow fuses. Products like large, powerful stereo amplifiers, the main fuses in those would be typically a slow blow fuse, because there may be times that the amplifier draws much more power when it's operating, especially at high volumes, and you don't want the fuse to be blowing every time it does that, and those are very brief and instantaneous increases in the amount of power the amplifier wants, and so that's fine. But in something like the 801T, you want a fast acting fuse because it's primarily there for safety. And the intercom system, the 4406, it's not going to be drawing huge amounts of power for very brief amounts of time. It, for the most part, draws about the same amount of power from the transformers all of the time. So a slow blow fuse is not necessary or the best choice. Also, if you were to have a dramatic failure in the 4406, it would take much, much longer for a slow blow fuse to finally give way and kill the output of the transformer, and that could be enough time that you could have other collateral damage from the damage to the 4406, which could potentially cause a fire. Also, the other consideration is this transformer was UL rated with a fast acting fuse, and since we don't want to violate the UL rating on it, we're going to replace it with exactly the same type of fuse, and any other choice than this would be negligent and a hazard and should not be done. So that's your warning. It's all up to you. It's your risk. It's your house. So, you know. Anyway, this is the type we're going to use, and what we're going to do now is we're going to install this in the 801T and try to replicate how the other one was done. So if we went back and reviewed the video, what we had was the original fuse sat here in the tape, and there's actually sort of an indentation in the tape here from where it was held in place, and if we put that as the new fuse in the same place, and we take the one end of the fuse and we carefully bend it around to the large copper wire, and then we carefully twist it pretty much like it was done before, that should be fine. That wasn't very complicated. So now what we need to do is prop this up. How's that? And we need to solder this, just like we did, just like it was done before. So we've got our soldering iron, and we've got our solder, and we have our visor so we can see it up close, or at least I can. And all you have to do is heat it up. And flow the solder on the twisted joint, and that's it. That part's done. Now we have a little bit of an extra end here, so we're just going to clip that off. And then the other thing that was over this before was this piece of braided insulating tube, and we're going to put that back over it like it was. And the reason they have that is you don't want any part of this shorting out on any other part of it. So we're going to put that like that to cover up the soldered end, which is good. But because I'm kind of a belt and suspenders kind of guy, we're going to do a little more to it than that. So I've got some of this. This is heat shrink tubing, and it's just a piece of tubing, but it's heat sensitive. So what we're going to do is we're going to cut a little piece of it. We're going to make it a little bit longer than the woven part. And we're going to slide it down over it like this. And then we're going to take our, this is a hot air tool. This is not designed primarily for heat shrink tubing. It is designed primarily for doing surface mount component work repair on boards that have surface mounted components. And basically over there is the main unit. It's a Heiko 850D, and basically what it is, it's a fan. It blows air out of the tip, and it gets very, very hot. Right now it's up to 690 degrees, 700 degrees, and it's going up and up and up. And it's at 740 degrees, which is a good temperature when you're desoldering electronic components off a circuit board, but it also works really well to melt the heat shrink or shrink the heat shrink tubing. So heat shrink tubing does exactly what it says. It shrinks when it gets hot. Like that. How's that? Pretty good. So now we put the woven plastic or woven cover over the joint, and we put a little bit of heat shrink tubing, which when it shrinks around everything and grabs it really tight, so it's going to stay in place and that little woven cover is not going to fall off. So that's just added protection to make sure that it stays good. Now, as this was before, the fuse sits right here, and the other end of the wire, this is the end that has to go through the hole in the cap. So what we have to do is we have to sort of bend this around, and we have to duplicate kind of how this one is sticking up, because we have to stick it back through the hole when we put the cap back on. So all I'm going to do is I'm going to bend it around and sort of curve it and make the end of it stand up like that. And that's pretty good for right now. Now, none of this wire from this side of the fuse, or this little piece of wire at this end of the fuse, or this piece of copper wire here, none of that was covered up or insulated or anything like that. So it apparently is not necessary to do that, and that to a large extent is what the tape is about. So what we're going to do is we're going to fold this down like this. So we have this sort of neat little compact package here. And then we're going to sort of fold the tape back over a little bit. But now the tape is all kind of frayed and stuff. So we have to fix that. So how are we going to do that? Well, we're going to do it like this. We're going to use this. This is Kapton tape. And Kapton tape is used in electronics a lot. And the thing that's interesting about Kapton tape is that it has good insulating properties, but it also has high resistance to heat. And this particular Kapton tape right here is rated for up to 752 degrees. So let's do a little demonstration about Kapton tape to show you how special it actually is. Okay, so here's our Kapton tape setup, our testing setup. So what we have here is, you can see the transparent yellow Kapton tape here, and here we have our standard black vinyl electrical tape that everyone is really familiar with. This is some Scotch Super 33 Plus electrical tape. This is good quality electrical tape. This is what Joe the electrician is going to carry in his tool belt when he comes out to your house to put up a chandelier. It has good stretchability, so when you wrap it around something you can stretch it and it holds tight. It has good adhesive on it. This is like a $5 roll of electrical tape, which is pretty good because you can buy it for 49 cents and it's no good at all. So it's good quality stuff. But what happens to it when it gets hot, so the hot air gun, the Heiko 850D, it's up to 740 degrees Fahrenheit, and if we put it on the black electrical tape, watch what happens. It's melting, it's sagging, it's falling apart, and it's actually smoking a little bit. So it's not designed to hold up to high extreme temperatures like 740 degrees. Now let's try the hot air on our piece of Kapton tape, which is, I'll point out, just half as wide. So if we do the hot air on the Kapton tape, still waiting. Oops, can you see? Still waiting. Nothing's happening. It is wiggling a little bit from the air blowing out of the hot air tool, but nothing is happening to it. Why isn't anything happening to it? Because it's designed to withstand up to 752 degrees Fahrenheit, which is also 400 degrees Celsius for those of you who do it that way. And you can hold it here till the cows come home. It's not going to melt, it's not going to shrink. It's designed to be stable under high temperatures. And that's exactly what you want. I'm going to turn this off now. That's exactly what you want when you have an application like a transformer, which is not going to get up to 752 degrees inside, but they can get fairly warm or hot inside. And you don't want to use vinyl electrical tape because the adhesive is going to fail, the tape is going to fail over time. It can shrink and deform from the heat, and you're going to lose the reason that you put it in there in the first place. So that's why we're going to use the Kapton tape. Those ends are really hot. How about that? Alright, so let's get back to our transformer. So what we're going to do is we're going to use the Kapton tape. We're going to start by using it to sort of mend back the yellow tape, the original tape that we kind of cut apart to get to the fuse. So I cut a little strip of it and we'll put it on here like this, and we'll sort of pull it down, and we can use our screwdriver and kind of tuck it in there a little bit, and we'll get rid of this little scrap piece that's in the way like this. And since you get a lot of this on the roll, you don't have to be chintzy with it, because remember, this is all about the safety. Safety is important. We don't want a problem. So we'll do that, and I think we'll take another piece and put it on the edge here over our joint. You know, really the purpose of all of this is to help hold it all in place. Now see, it's flopping there a little bit, which I don't really like, so I'm going to take a short piece and I'm going to put it this way and hold that down. Okay, so now that's all pretty secure. Then we'll take another piece and we'll fold this down, and then we'll take this outer piece of tape that has the red insulating cardboard inside of it, and we're going to fold that back down and put some more, because we really want to put this back together very much like it was before we did our fuse-ectomy. I guess now it's not a fuse-ectomy. I guess it's more like a fuse transplant. You know? I don't think anybody else is doing fuse transplants that I know of, but could be. We'll put that. I don't think we need that little piece, so we'll put a little more. And I suppose that if you're really good at wrapping Christmas presents, you'll probably be pretty good at this. We'll do another piece. There's really no reason to be chintzy with this. You're only going to hopefully ever do this one once. And you really want to kind of seal it all together. So I think I'll take another piece. In fact, I think what I'll do, put another one like this. Alright, so that should be pretty good. I think that's all pretty well sealed up and held in place, and it's not going to move around, and it's not like you're going to be swinging on it with a rope. You're just going to, it's going to sit there. And to some degree, when you put the wires back through the end caps and solder them back in place, that's going to hold the loose ends of everything together, and I think it will be fine. Now, one of the things I want to do before we try to put the end cap back on is on this heavy piece of wire right here where we desoldered it, there's a little bit of rough solder buildup. And I'm just going to take the soldering iron and see if I can take some of that away and smooth it out, because the more you do up front, the easier it will be to put the end cap on. The other thing I'm going to do is, if you remember, originally it was bent over a little bit, and I think the straighter we make it, the easier it will be to put the end cap back on. So let's see how close we are. And one of the things to notice is the tabs with the holes, they're offset. They're not in the center of the red insulator. They're biased towards the left this way, and so are the wires. So you have to put it on the right way. And what you can do is, this part's a little tricky because you have to get the wires through the holes. And the easiest way to do that is to try to sort of get them lined up as close as you can first. And then, and see, this one, the small one where from the fuse, is longer, so you can get that one in first. And then hopefully you can see the other one, which is it's sitting right here at the bottom of the opening. And I need it to come up through the opening, and it doesn't really so much want to. So let's take this back off. And I think what we're going to do is we're going to see if we can clean up the solder on it a little bit more, so it's more just wire and not so much solder. So you can see in the close-up here, there's a certain amount of solder buildup on the end of the wire, and so it makes the diameter of the wire bigger than it is without the solder, and we need to clean that off. And a good way to do that in this case is, first we're going to heat it up and we're going to put a little fresh solder. Because adding fresh solder is a really good thing to do sometimes. It makes the world a lot simpler. And then we have this. This is desoldering braid, and it's woven copper braid. And what it does is you put it on the solder joint, on the solder, and you heat it up with a soldering iron, and it sucks up or wicks away the solder that's on the wire. Pretty good stuff. And so now, instead of the solder on the wire, the solder is on the solder wick. So you can see down here it's still copper, but up here it's all silver because it's full of solder. And now the end is a lot cleaner, and that's better. The other thing I think I'm going to do is I'm going to very carefully snip off just the littlest bit on the end, because I think it's a little deformed, and that's going to keep it from going in the hole. And then the other thing I'm going to do is I'm going to lift it up a little and bend it over a little more, bring it up a little higher essentially, because that will, I think, make it easier to get it through the hole. So if we get the little wire in first, and then we sort of jockey everything around. So the trick is, if you can see it, you might be able to get it through. There we go. See? That was, did you hear that? It popped through. And now you can see I've got a little bit of the heavy wire right here sticking through, and a little bit of the thin wire over here sticking through, and that's exactly what we want. So what I'm going to do now is I'm going to pull the heavy wire up just a little to get a little more, and I'm going to very carefully bend it over just a little, like it was before, because that's going to do two things for us. So now it's bent over. I didn't bend it over all the way flat because I want a little space under it in case one day I got to pry it up again and I get my screwdriver under it. And then we have the thin wire, and we're going to do the same thing. We're going to bend it over, and because it's a little long, at the end we'll clip it off a little bit. So let's lean this like this. See if we can get this to stand up. See, it wants to fall over because it's heavy. Alright, so now guess what we're going to do? We're going to solder the wires back on, just like it was before. So we'll do the heavy one first. So we'll heat it up with the soldering iron. You want solder in the hole where the wire comes through, and then you want the blob on the outside, and you want to catch your transformer before it falls over and all the solder goes falling off the joint. So there's one side. See? And now we'll do the little side, and it's the same thing. You want solder in the hole, like that, flowed in, and then a blob. Now this wire, it's sticking up some above the tab, which I don't really want. See, sticking up. So what I'm going to do is I'm going to heat it, and I'm going to push it down into the solder, and then I'm going to hold it with the screwdriver until it sets, and there it is. Okay, so now our end cap is back on. And we'll clip off the little extra because you don't need that. So that end's done. So now we have replaced the fuse, rerouted everything like it was originally, put the end cap on, and soldered it to the low voltage screw terminals. So the last thing is the next thing is we have to put the other end cap back on. And this part's pretty easy because we have to put our red cardboard insulator back on, and all you have to do is put the wires through the holes. I think this one goes this way, and this one goes this way, and slide them down, and it just sits on there like that. The folded over end is folded over the primary side of the coil, and then you take your end cap and you put the wires through the end cap. And you slide the end cap back down and pull the wires through so they're not bunched up inside. You can see, if you look carefully, inside the hole right here, you can see a little bit of the red insulating card and the hole that the wire comes through, and you can see how when it's all in place, the red cardboard keeps the wire in the center of the hole so it doesn't chafe on the edges and wear through, and that's the purpose of it. So it's important to put that back in. So now what we have to do is we have to bolt all this back together so it becomes a usable thing again. Okay, so this is how we're going to put the ends back on. If you remember in the beginning, we drilled out the rivets, and we're not going to redo rivets because I'm not actually at that point with doing this at the shop yet where we can re-rivet, but that is something we're working on. So for today, we're going to use some threaded screws and nuts and washers. So we're going to take the screws and put them through the holes, through the end caps, through the laminates, and there. We're going to put some star washers. These have teeth on the inside because that's the kind I like. We'll put the star washers on, and then we have a nut. And we will fold it together. And to start with, we'll just snug up each one a little bit because we want to be able to wiggle it around a little bit if we have any problems with getting the screws through the holes or anything like that. Those two, and one. I know it's kind of hard to see, but you can only keep your hands out of the way so much because I do have to actually get the nut on the end of the screw, but if I hold it like that you might be able to see. So this is the fourth one, and once we get them all in place and everything looks like it's lined up correctly, we can go ahead and tighten these down. You don't need to super wrench on them. I imagine that the crimped over rivets were pretty tight, and it is important to have it reasonably tight because one of the purposes of this is not only to hold the end caps on, but it also helps squeeze the laminations of the core together so they don't separate and it doesn't get buzzy sounding when it's turned on. Now it's all bolted back together. As a note of interest, and I'm not doing it on this one in this video because I still may want to take this apart later on. One of my considerations in a project like this is, or the primary consideration in a project like this, is safety first. everything we do has to be done safely so it doesn't create a problem sometime in the future for whoever we're doing this for. If we do these, or when we do these for customers that have 801Ts with blown fuses that need to be replaced, we are going to take some extra safety precautions to make sure that the transformer that we repair and send to them stays the way we did it. And what I mean by that is the very worst thing that anybody could do, and there are people out there who think they know way more than everybody else, is to take this all apart, get rid of the fuse, put it all back together, and put an unfused transformer back inside their wall. That would be a reckless and dangerous thing to do, and you're inviting disaster, and you could possibly burn your house down. And I'm actually going to take one of these 801Ts, and I'm going to take the fuse out of it, and I'm going to wire it up on a short on the low voltage side and power it up and show you what happens when a powerful transformer fails and there's no fuse. Because that should be a warning to everyone that you should never ever change something like this. It was done this way for a reason, and although there are people who think they are smarter and know more than everybody else, those are the ones that their house is going to burn down. And because I'm not going to be responsible for that happening, I'm going to repair this the way it was done originally. And to help ensure that no one modifies the work that I've done, when we do one of these for someone, for a customer or something like that, we're going to take some extra safety precautions. We're going to put thread lock on the screws and nuts, which will make it much more difficult to disassemble. And then we're also going to take and put a product on the screws and on the heads of the screws that is basically, it's a tamper indicator. It's sort of a thick gel material, and it goes into the threads and over the tops of the nuts, and it goes into the heads of the screws on this end, and when it dries it becomes hard and brittle, and if you were to try to disassemble this transformer by unscrewing the screws, the tamper material will break and chip away and fall off, and it won't be there anymore, and then it's obvious that it's been disassembled. We will eventually get to the point where we will be redoing the rivets. And when we do that, the tamper-proof probably won't be necessary, because if you drill out rivets, they're done, and most people don't have the ability to re-rivet it. It's even something that's going to be challenging for us to set up to do correctly. So that's some of the extra safety measures that this will require. But anyway, for today, this transformer has been repaired, at least in theory, because we haven't actually tested it yet. So that's what we should do next. So here's the setup. I have the 801T that we just repaired, and it's wired to my bench AC power supply, and I have the AC power supply set at 115 volts, and we're going to turn this on, but first I'm going to show you the voltage on the meter. So you're looking at the display readout on my Agilent or Keysight 34461A multimeter, and everything is turned off and the probes are not touching anything. So I'm going to turn on my bench power supply. It's on now, and I'm going to touch the contacts on the terminal strip where the transformer is connected for the line voltage, and you can see we have 114.3 volts. So I'm going to bump this up just a little bit to 115, because that's what you would most commonly have in your house. It's a little high. See if we can get it down just to right it up. It's a little touchy. Okay, that's pretty close. 115 volts AC line into the transformer, and now I'm going to put the probe terminals on the output connections, the output screws on the secondary side of the transformer, and we have 19.1 volts, which is well within specifications. We don't know precisely what it was before the original fuse blew, and it is an 18 volt transformer, but it's putting out 19.1, which would be fine because there's no load on the transformer. It's just running free. So now we have a properly working 801T because we've replaced the fuse. And I guess what I'm going to do is I'm going to show you that the fuse does actually work. So I'm still measuring the secondary output of the 801T, and I'm going to take my screwdriver, right here, and I'm going to short across the screws, and I'm going to blow the fuse, and I'm going to do it on purpose. How about that? So here we go. It's on 1 and 1, 2, oops, it got stuck. 1, 2, 3, short circuit, 0.9 volts. So we blew the fuse inside the transformer, and essentially we're right back to where we started. The transformer is now dead, and that's how fast the fast acting fuse goes, and that's how fast it happens when you're trying to disconnect your 4406 from a transformer and the wire slips and there's a spark and it goes dead, or when the 4406 overloads the transformer and blows the fuse. But at least it didn't cause a fire and your house didn't burn down. So Harvey wants to know, oh, have you met Harvey? This is Harvey. He's a hedgehog. He's our shop mascot, and he's our executive producer of all YouTube videos. Harvey's outraged at the moment. You can probably tell if you look at him carefully how outraged he is. He said, we spent all this time and effort to repair this transformer, and then just out of the blue, I short it out and blow the fuse, and we're right back to where we started again. But there's a reason why I did that. I said I was going to make a video that shows you what happens to a transformer when you overload it without a fuse, and that's going to be this exact transformer. It's not going to be in this video, it's going to be in another video. Or no, I think I'll splice it into this video. As promised, I said in an earlier part of this video that I was going to try to show you what happens if you remove the As promised in an earlier part of this video, I told you I was going to show you what happens if you remove the safety fuse from an 801T transformer and you have a dramatic failure that overloads the transformer. While I'm not willing to blow up a perfectly good transformer because that would be hugely wasteful, especially for something that's really hard to come by nowadays, I was able to find at the shop this 801T. This 801T is marked in a special way. It says down here, buzz. And this 801T actually came out of one of my customers' homes locally, and the complaint with it was, it buzzes, and it buzzes a lot. So, well, at least in her house it buzzed a lot. So a buzzing transformer, the buzzing is caused by problems with the laminations in the core here, where some of them inside most likely have separated or they weren't squeezed together properly in the first plate, and it creates a transformer that buzzes. Even though this transformer has the correct output on the low voltage side, nobody wants a buzzing transformer. You can't put it in somebody's house because it'll drive them crazy. And part of the reason why is these transformers mount onto a metal bracket, and then they slide down inside the metal can, which is mounted inside the wall housing, and it sits next to the back of the drywall. And so a buzzing transformer on a metal bracket in a metal can amplifies the buzzing, and then you put it inside a wall cavity near the drywall. It kind of acts like a drum, and it becomes even louder. This is going to be our sacrificial transformer because nobody wants a buzzing transformer. It doesn't really have any use. I could use it here at the shop because I don't care about the buzzing, but I have bench power supplies and I don't like moving heavy transformers all over my workspace. So this is going to be our sacrificial 801T, and just to show you that what I'm saying is true, I suppose, I'm going to let you hear it buzz. So I'm going to turn it on and I'm going to hold it up to the microphone so you'll be able to hear it. And let's see. Yep, buzzing away. Okay, so hopefully you were able to hear that. So I'm going to go ahead and stop the video. I'm going to modify this and bypass the fuse, and then we're going to set it up and we're going to see what happens when we overload it. Okay, it's time for our test. So here's what I've done. I've taken our 801T transformer, I disassembled it like I showed in the earlier part of this video. I removed the fuse, and then I rerouted the outputs of the secondary and soldered them back onto the two screw terminals. And the way I decided to test this to sort of make it equivalent to what might happen inside the wall of your 4406 system is this red and white pair right here, which is screwed onto the terminals of the transformer. This is an actual power lead cable from a 4406 power module, and what I did on the end here where the little white connector is I just took the pins that would go through the circuit board and I bent them together and soldered them. So basically what we have here is a dead short. I'm doing this outside because I was specifically asked to please not do it inside the shop because we don't know what's going to happen exactly. I don't really know what's going to happen. Either it's going to be really good or it's going to be a total dud. I have no idea. But the point of this part of the video is you should not modify the transformer. You have to leave the fuse in it because if you don't, it's a safety hazard and you could burn your house down, and we don't want that to happen. So I have the transformer wired up on a pigtail cord, and it's plugged into another cord, and in here in the shop it's wired to a switch so I can flip it on. So I guess here we go. We're going to flip it on and see what happens, because I don't know what's going to happen. It should be interesting. Maybe it'll blow the breaker and all the lights in the shop will go out. I don't really know. Anyway, here we go. 3, 2, 1, go. And I think the wire is getting hot because you can see it move. And I have a feeling what's going to happen is maybe it's just going to make the wire get really hot and it's going to melt the insulation on the wire, or maybe the transformer is going to blow. I don't know. See? That's what I said. Could be a real dud. Maybe nothing's going to happen. But I bet the wire is pretty hot. I don't smell anything. See, we were all hoping for like smoke and flames and an explosion. It would never explode, but it could smoke and flame. I would imagine it's probably pretty hot. So let's review what we've got here. The transformer is still powered up. I took my multimeter. I have a thermal probe here, and it's inserted inside one of the rivet holes. So it's reading the internal temperature of the transformer, which is now at 158 degrees, 159. It'll go back up to around 165 if we leave it long enough. And the point of this was to show you what could happen if you modify the transformer and take the fuse out. The fuse is a safety device, and the transformer is UL rated for the fuse inside the unit. The point of this part of the video is don't modify the transformer. Don't take the fuse out. It's a safety device. What you have to think about is that while we didn't get flames and sparks and smoke and running and screaming because the transformer blew up dramatically, what we have here is a transformer that's on full overload. It has 0 volts output because it's putting out to a dead short. The wire is very hot. The transformer is up to about 170 degrees. The breakdown temperature of a varnish or enamel magnet wire insulation is around 250 degrees. So we're not quite at that point, but it does seem to be going up. The other thing you have to think about is right now in this test, it's running out in the open and free air, and there's a little bit of a breeze, so that's helping keep it a little cooler. What you can envision is these transformers are mounted inside a metal enclosure, inside the wall housing, inside the wall of your house. And if you had 2 failed transformers, and if they're both putting out to a dead short because you've had a dramatic failure in your 4406, you would have 2 fairly solid blocks of metal sitting inside your wall cavity running right now at 175 degrees, which is pretty high. And since it's inside the wall, the temperature is going to go up even higher because there's no cooling inside the wall. So it's going to get very, very, very hot. And at some point, I think, if we left it long enough and created a more realistic installation as it would be in your wall, I think it's going to go up and up and up, and eventually I'm pretty sure the insulation on the magnet wire is going to fail, it's going to short out, and I think that's when you get the smoke and the sparks and the flames and the running and screaming. So is it really worth it? Is it really worth taking a chance to burn your house down because you didn't want to pay a few dollars to get your transformer fixed? I don't think so. So we're up to 180 degrees now, so it seems to be going up higher than it did before. This wasn't as dramatic as I guess everyone would have hoped for, but the point is still made. Don't fool with the transformers, don't take the fuses out, have them repaired properly so that you don't have a problem and you don't burn your house down. So I've let this run since the last segment just to see what would happen as I clean up things in the shop a little bit. We're up to 188 degrees right now, almost 189. I'm going to let it run for a while because I have a few things to do. If we get up to 200, then I'm going to stop. The temperature seems to be going down a little bit. Although 186 is still pretty hot. We're up to 194 all of a sudden. Alright, so I'm going to call this now because I set sort of an arbitrary maximum, which was 200 degrees, and while I was getting set up to do the next bunch of work here at the shop, we have now exceeded 202, or it was 203 a few seconds ago. There we have 203 degrees Fahrenheit of the transformer as it sits there cooking itself to death. So I will make the point one final time, since we're about 25 degrees higher than the last time I set it. Do you really want two solid metal cubes inside your wall, sitting there running at 200 degrees Fahrenheit, so hot you couldn't possibly touch them. And I still have the feeling that if we left it long enough, it's going to have a sudden failure, and that's when we get the smoke and the flames and the running and the screaming. So I'm going to shut this down now, but this should be enough to show you that taking the fuse out and bypassing it, it's a bad idea. Don't do it. So Harvey's outrage will subside, as it always does. I hope you found this video to be interesting and helpful. If you did, please give it a thumbs up on YouTube. If you have an 801T and it has failed and you're in search of one, get a hold of us and I'll talk to you about you sending it to me, and I'll repair it for you, and you have a working transformer. That's all for today. See you on the next video.